Hello everyone. In this video, I will give you more insights about the computation of the slope out of the digital elevation model. So this is the map we have created together. And that's basically all the data we have. We have H, it's a 2D array that contains the altitude. We have XC, which is a 1D array that contains the X coordinate, and YC, which is also a 1D array that contains the Y coordinate. So that's the data layout. We have NCX times NCY cells, and at the center of each cell we have the blue dot that contains a value of H, the altitude. The XC array can be represented as such. It's a 1D array that contains the position of each of the centroids of the cell in the X direction. So that's the size NCX. We also have a 1D array, YC, which contains the Y position of each of the centroid of the 2D mesh. The size is NCY. Now we want to compute the slope. So let's introduce the gradient of H. So the gradient of H is a vector, has two components, Hx and Hy. So Hx is dH dx and Hy is dH dy. In short, one can use a simple function called diff that exists in MATLAB, Julia, or Python, which will help you to compute differences between 2 points. So diff of h, dims equal 1 divided by dx will give you an approximation of the slope component hx. Dims equal 1 stands for the dimension. Dimension 1 in our example corresponds to x, and dimension 2 corresponds to y. For the y component, one can write diff h, dims equal 2 for the y direction, divided by dy. dy and dx are the discretization steps that define the resolution of the model, and they can be computed, for example, by measuring the distance between 2 points along the x direction for the x and 2 successive points in the y direction for dy. So dx can be written as xc position 2 minus xc position 1, and the same for yc. So we are back to our data layout. We have the blue dots for H, and we now have the red bars for Hx. So that's the expression we can use to compute dH dx or Hx, diff h, dims equal 1 divided by dx. So what's happening under the hood, what this thing is doing here is similar to using slicing very explicitly here. So this expression would be the same as this one. So in your notebooks, use either this one or this one. You can choose which one you prefer. And here, we basically subtract 2 parts of the arrays to make the difference. So let's start. We have Hx is h from 2 to n, colon, minus h1 to n minus 1, colon, divided by dx. So this part here is basically the selection of the points in the H table that start from index 2 in X, and we take all the points in Y. So it means we select only this part of the array, and this whole column from index 1 in X is not selected. From this one is subtracted the second part, h1 to n minus 1, comma, colon. So now we start from index 1 in X, and we reach index n minus 1 in X. And all the points are selected in the Y direction. So now we have this entire part of the array. The two of them are being subtracted from the other and divided by dx. And that gives us the slope component hx. Now we do it for the y component. For the y component, we have now these vertical red bars. They are located in between the blue dots in the y direction. We have this expression, diff h comma dims equal 2 divided by dx, which is similar to this expression, hy is equal to h colon comma 2 to end minus h colon comma 1 to n minus 1. So what does it mean? The first part, h 2 to end in y. We are selecting all the points starting from index 2 to end in the y direction. And to this is subtracted this portion of the array starting from index 1 in y to index n minus 1 in y. So index 1 and minus 1 in y, this entire part of the array. By doing this operation, we can approximate the slope component hy, and we end up having all our slope component hx and hy living at different places. So how can we visualize this information when all the slope components are living at different locations? And the answer is to interpolate the information. So we are going to interpolate the red bars to the vertices, the crosses of the intersection of the grid lines, the black grid lines. So there's going to be an interpolation of the horizontal component of the slope, hx, vertically to this point, and an interpolation of hy horizontally to reach the same set of nodes. So how to proceed? We are going to make a simple average. So let's start with hx. We want to compute the value of hx at this location using this data. So we can take half of these nodes plus half of these nodes. That's an averaging. So here's an expression for this. 1/2 of hx, we take all the nodes in x, comma 2 to end in y, plus hx, all the nodes in x, comma 1 to n minus 1 in y. So let's go step by step. The first part of the array is again now taking all the indices in x, but starting from the second one in y. So we basically cancel out this line here, and we take this whole part of the array. The second part here has all the indices in x, but in y it starts from 1 and ends at end minus 1. So we take from index 1, we reach the end of the array minus 1. That defines this part of the array hx. So the sum of these two arrays divided by 2 will give us the interpolated value of the slope hx at the vertices. Let's do the same for hy. So for hy, we have a horizontal interpolation that can be written as half of hy index 2 to end, comma, colon, plus hy index 1 to n minus 1 in x, comma, colon, in y. So we can do it step by step. Let's look at the first term. h2 to end, comma, colon means we start from index 2 in x and we reach the end of the array in x. So we do not select these points. We start from this and we take this whole part of the array, hy. The second part here basically means we start from the first index in x, but we will not select the last column. So we start here and we do not take this one. We restrict ourselves to this part of the array. So the average of these two subarrays will give us hx and hy. Look at the location of the green dots. So now we have interpolated the slope components on the green dots. To visualize the information, so we have a new array of two new arrays, hx and hy. To visualize this information, we need to know the coordinates of the green dots. So let's think a bit. Remember, we have for the coordinates the xc array. So the xc array has ncx dot in the x direction. It's a 1D array. And the green dots are always located halfway between the blue nodes. So they're always in the middle. So in fact, these nodes, which we will call XVI, are simply can be defined by the interpolation of xc node of xc to XVI. So we can average the coordinate xc and we will obtain the location of the XVI node. So if I take half of this point plus half of this point, then I will get the location of this point. If I take half of this point and half of this coordinate, I get this coordinate here. So this can be done by 1D interpolation. So XVI can be defined as half of xc from 2 to n plus xc from 1 to n minus 1. The same would apply to the yc and yvi nodes, which are here. So we have this set of nodes, and to compute the location of the vertices here, it's simply the average of these coordinates. So we can average the coordinates and we will obtain the position of the set of green nodes. So that's just to summarize the computation of the slopes, or the average of the slopes. So we do one average in y for hx and one average in x for hy. This will average the slope at the inner vertices, the green dots. Then we want to compute the slope. So we will basically take the norm of the vector of the gradient of h. So we take the square root of hx square plus hy square. So this can be simply written as dh is square root of hxv square plus hyv square. So these are, of course, arrays of similar sizes. These are the interpolated slopes components. So then dh will also have the same size as hxv and hyv, and it will contain the norm of the gradient of h at each point of the map. So what's a slope now? Let's think in 1D. We have h is a function of x. So h can be written as a times x. It's a linear function here. So a is dh dx. And the slope can be defined as the arctangent of a, which is here same as the measurement of the slope. So if you want to compute the slope, you can basically take the arctangent of the gradient of h, the norm of the gradient of h. In all the language we consider now, there are two functions that can be used for trigonometric computation. So if you use tan will require using angles in unit radians, and tan d will allow you to use angle in unit degrees. So you can use either of these two functions. The inverse tangent, or the arctangent, is simply defined as a tan or a tan d. So in the end, you can now plot the slope that you've computed. To plot the slope, then you will use S transpose, and you will need to use the coordinate xvy and yvy. Thanks for your attention.